Hey everybody, Vade here, back in with another calculus preparation video. Today I'm just going to be showing you some algebraic techniques that you need to master. Of course, this is not the only video that I'm going to make regarding this. These are just 4 techniques that came right to me, but I will make more. So this is sort of, think of it like a part 1. Okay, so as you see here, I'm presenting 4 in this video specifically, and you see the stuff in the parentheses here. These are sort of just the calculus linkage, like when do we use these techniques in calculus specifically? Because again, this is just part of my no BS approach to preparing you for calculus. I want you to only learn the stuff that you like really need to know and master beforehand. And of course, like some of these are not necessarily required. I feel like calculus classes will, of course, go over a lot of these techniques beforehand. But I still think that it's to your advantage because it'll just be easy peasy for you going forward. But of course, a lot of calculus classes are sympathetic with the fact that, like, if, let's kind of quickly review this before learning this sort of thing. They're not too strict about these things. Like, if you don't recall it as well, like, of course, you should have seen these techniques before. But they will usually go over it. But I'd recommend just knowing it off the bat and doing it correctly, okay? So, anyway, let's start off with the solving higher degree inequalities using the snake method. And you're probably like, what the heck is a snake method? We're going to talk about, like, why it's called that. Like, why do we call it the snake method? Not everyone calls it that. That's just how I learned it. But again, you'll sort of see it as we go. Like, it'll form a snake. But this is important just for, like, calculus optimization problems. We talked a bit about optimization in the previous videos, geometry needed for calculus, where we actually, like, find these relationships and stuff like that. And I kind of talk about how that can be used to actually find the maximum or the minimum of something. So of course, you will, like, again, need to solve higher degree inequalities, especially if we have something like this. Let's say we have some volume equation, and it's just x times 4 minus x times 9 minus x, like a length times width times height scenario here. You want to make sure that the volume is, I'm just going to say in this case, the box has to exist. I'm going to think of it like a box, right? This is the equation for the volume of a box. And it has to be greater than 0. So in order to do that, we need to have the inequality. We just need to have this volume expression always be greater than 0. So just x times 4 minus x times 9 minus x. This must be greater than 0. Okay? And of course, this will be like a higher degree inequality. What I mean by that is greater than 1, a degree greater than 1. Because if you have like an inequality like this, like x minus 5 is less than 0, you can easily solve that. So I'm not going to go over that. But if you get into stuff like degree 2, degree 3, etc., that's where it kind of gets a little more complicated. And we need to use methods like the snake method in order to do it. So we have this inequality right here. So what I want to do first is set each of the factors equal to 0. So I want to let x equal 0, 4 minus x equals 0, and 9 minus x equals 0. So once we do that, we should get x equals 0, x equals 4, and x equals 9. So now I'm going to draw a number line here. Let me make it a straight line. There we go. So it's like a number line here. And I want to actually put these values on. So I'm going to say that this is 0, this is 4, and this is 9. So it's crucially important that you put it on it as an open circle, because it is greater than 0. It's not greater than or equal to 0, right? If it's or equal to, then we would shade it in and put it as a closed circle. Hopefully recall that from Algebra 1 or Algebra 2 class when solving just inequalities in general. Like, for example, degree 1 inequality, like x minus 5 is less than or equal to 0. You'll have like a closed circle if you graph this inequality right here on the number line. So same sort of thing. So now I just want to put these factors here, like on the left side here. Like I want to put x, 4 minus x, and 9 minus x. The order at which you put them in does not matter at all. Like, I could flip-flop this and rewrite it as x, 9 minus x, 4 minus x, right? The reason why is because we will just be doing some multiplication, and of course you can rearrange the order of multiplication. That is completely allowed. Okay, so now I'm just going to write negative infinity here and positive infinity here. The more you do this, you just sort of expected that, negative infinity and positive infinity. You don't really need to write it down, but we're learning, so I'm just going to do it anyway. So now we're going to do it as such. So I'm going to pick this first row here with the x. I want to then think of these as like sub-intervals, okay? I'm going to put these as sort of sub-intervals here. Okay, like sub-intervals. Okay, let me make it more like this because it's infinity. Okay, so sub-intervals here. So with x, for this first sub-interval here, I want to pick a value between negative infinity, pick a yellow here, negative infinity and 0, and plug that in for x. So between negative infinity and 0, I'm going to pick negative 1. Negative 1 is negative, right? Because we plug in negative 1 for x. X is negative 1. That's a negative value, so I'm just going to put a I'm just going to put a negative sign here. Okay? Sounds good. Let's then do the same thing here with this subinterval with 0 and 4. So then plug in any value in for x between 0 and 4. I'm going to pick 1. That will be positive. So I'm going to put a plus sign here. Why do I keep changing this color? Oh, okay. Then, of course, from 4 to 9, I'm going to pick 5. That'll be positive as well. And then from 9 to infinity, this will then just be I'm going to pick 10. This will then be also a positive value, right? So hopefully you understand here, just picking values in for x from the subinterval. So negative 1, negative. I picked positive 1 here, should be positive. I should pick positive 5 here, should be positive. I picked positive 10 here, it should be positive. Sometimes it helps if you actually pick the numbers that you use here. Like I'm gonna actually write it here. Like I picked a positive, or I picked a negative 1 here, I picked a positive 1 here, I picked a positive 5 here, and I picked a positive 10 here, and that's why I'm taking these signs here and just writing it down. The signs. Just gonna circle them. So same thing here, but now let's use 4 minus x. So pick any value in for x. I'm going to use the same numbers, actually. So negative 1, 4 minus negative 1 is positive 5, so it'll be a positive value. 4 minus positive 1, that's 3. So that'll be also a positive value. 4 minus positive 5, that should be a negative value. And 4 minus positive 10 should also be a negative value. Okay, hopefully you understand. 4 minus minus 1, positive. 4 minus 1, positive. 4 minus 5, negative. 4 minus 10, negative. 9 minus x, so 9 minus negative 1, positive. 9 minus 1, positive. 9 minus 5, positive. 9 minus 10, negative. Okay, so now I want to draw another like horizontal line here. And now what I want to do is I want to multiply the signs. I want to multiply the signs. And again, that's why I said it doesn't matter how you arrange the terms here on the left side, because multiplication can be rearranged. So we have a let me pick a color, different color here. We have a negative times a positive. That's a negative times a positive. That's still a negative. Okay, right? Negative, positive, negative, negative, positive, negative. Positive times a positive is a positive, times a positive is still a positive. Positive times a negative is a negative, times a positive is a negative. Positive times a negative is a negative, times a negative is a positive. So our snake, which I'm going to write here, should look something like this. We have a negative also. I'm going to erase some stuff here now that we're done, just to sort of better illustrate the snake here. because now we have the signs. Okay, so now our snake should look something like this. So we have negative, then we have a positive, then we have a negative, then we have a positive, and that's how the snake method works. I'm going to erase these guys right here. Oops. Why is this eraser like that? Can I not erase? Okay. This eraser is so bad. Okay. Yeah, so hopefully you understand here that this is like our snake. Ooh. See this? Like a snake. So we have our signs here. So now, in order to find for what values of x will make this like true, here we want volume to the volume of the box to be greater than 0. Well, then x has to be, and then I'm going to say like our domain here. You can say x is an element of. That is technically correct notation-wise. I've just not been doing that in the previous videos, so just know that you should technically be doing that. But if you write domain here, I think it'll be fine. Oops. So now the domain, we see that we want x to be greater than 0. So if we want x to be greater than 0, we want to be looking at the positives here. So then we would say that the domain is from 0 to 4, union 9 to infinity. And again, like this is why open circles here means regular parentheses, not brackets. Now you can always check this just to see if you're uncertain here. Like if you plug in values in between these intervals, like if I plug in like 3 here into this volume of the box equation here, I plug in 3. We see that the output will be positive. If I plug in 1,000, the volume will still be positive. So that's why, you can just quickly check here if it works. Again, you can also do the guess and check process here. You don't have to do the snake method. I just feel like for most students, it's better just have like that defined way of doing it. And also it's better for teachers because they can give partial credit because they see like the clear process of how you like found the domain and how like, oh, it could have just been like, oh, you did a negative times a positive and then you said that that was like a negative or something like that, some simple mistake, and you would still get partial credit. So just showing all this work will be really beneficial to you in the long run, especially if you make a mistake. Your teacher can look at this work and see, hey, I know where you went wrong, but you did everything else right. And that's I can give you credit for that. Whereas if you just blindly plug in values in your head and you're like, oh wait, I think that it'll be positive here, you're just taking more of a risk. Okay, so the second way or second technique that you need to know is like just sort of some like shortcuts to expanding binomials. And we're going to talk about the difference quotient. Now, the difference quotient specifically relates to the limit definition of the derivative. Okay, but I'm just introducing you to that because sometimes, teachers introduce students to that before actually studying calculus. So you're probably like, whoa, wait, what, where does f of x plus h minus f of x over h come from? That actually is the, limit definition of the derivative. That's the slope of the secant line. Again, and then you'd put limit as h approaches 0. That would be the entire limit definition of the derivative. You probably have no clue what I'm talking about right now, but I guess the reason why is because they want you to have practice plugging in or evaluating this difference quotient. We're going to talk about that in just a second here. The reason why I'm not going to talk about necessarily the limit definition, the integral, it's a little more like you deal with summations and stuff, but that also, like, again, in the polynomial context, could involve like some foiling of a binomial. So that's why I just want to go over it and again, mentioning where these could be really important. Okay, so first of all, I want to go over some shortcuts for expanding binomials. So first is if you have like a plus b the whole squared. Hopefully you know that like you can just FOIL it out like this, a plus b times a plus b. When you have a degree 2, it's very easy to do it that way. Or hopefully you know that it would just be like an a squared plus 2ab plus b squared. You know, that's what it also equals to. Maybe you already know that like from just, you know, doing it so much, or like your teacher taught you to remember this. Okay, now do you guys know how to FOIL out a plus b the whole cubed? Maybe, maybe not. Maybe you know the formula. I do. It's a cubed plus 3a squared b plus 3ab squared plus b cubed. But let's say you don't. You can always FOIL it out like a plus b times a plus b times a plus b, but that will take like a while. Okay, there's a quicker way of doing it, and this is where we get into something called Pascal's triangle. Maybe you've heard of it, maybe you've not, but I'm just going to talk about it anyway. So what's Pascal's triangle? Well, it's a triangle, okay? So I'm going to start off with just drawing, like I'm going to write here, Pascal's triangle. Okay, so we're going to start off with a 1, and a 1 here. We're going to start off with 3 1s. Okay, there will always be 1s on the side here. So I'm going to put some other ones here. And then I'm going to do 1 and 1. I'm going to add them, and I get 2. I'm going to put more 1s on the sides here. Then I'm going to take this 1 and this 2 and this 1 and this 2. And this 2 and this 1. And I get 1, 3. I get a 3 here. And then it's just 1s. Then I'm going to bring a 1 here to the side. 1 here to the side. I'm going to do this 1 and this 3. I'm going to add them. This 3 and this 3. This 3 and this 1. This will just be 1, 4, 6, 4, and then the 1s on the sides here. So again, the algorithm, if you're having trouble sort of seeing it here, I'm going to do it one more time. Just put more 1s on the sides here, and then just add 1 and 4. This is 5, 4 and 6. This is 10, 6 and 4. This is 10, 4 and 1. This is 5. Okay, and it'll just keep going, right, like dot, 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 dot. This is Pascal's triangle. And hopefully you see here that, you know, because this is infinite, it will eventually, like, form a triangle. Okay, so this is Pascal's triangle. So you're probably like, how does this work then? How does this relate to a plus b the whole cube? So you want to pay attention here to the row number that you're on. So this is like row 1. This is row 2. This is row 3. This is row 4. This is row 5. Dot dot dot. Right. So you want to match the row number with your degree number. So this degree here would be 3. So then, or like, you get what I mean, like the exponent. It would be 3. And I want row 3, so we know that then we'll have coefficients of 1, 3, 3, 1. How did I know that it was the coefficients? A squared plus 2ab plus b squared. 1a squared plus 2ab plus 1b squared. That's how I knew. Okay, so then this pattern continues, and these are just coefficients. So again, a plus b to the 4th. It'll just be then, we'll go to row 4, and it'll just be, the coefficients will be 1, 4, 6, 4, 1. So it'll be a to the 4th, 1a to the 4th, and yada, 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 plus 1b to the 4th. So that's how you do it. That's how you get the coefficients. So where do we go from here? Well, we want to take each of these guys. So I'm going to start with a, and we'll go from a to the 0, then a to the 1st, then a to the 2nd, then a to the 3rd. Then I want to do the reverse with b. I want to do b to the 3rd, b to the 2nd, b to the 1st, b to the 0. And I just want to add, right? So then, if we actually do it here, we'll get b cubed plus 3ab squared plus 3a squared b plus a cubed. Isn't that what I got before? Well, yeah, it is. That's what we got. So now that you know Pascal's triangle, we're going to actually apply it to something called the difference quotient. So the difference quotient is something you use in calculus. It's, again, where it comes from, it's just going to confuse you. But thing is, in order to find the derivative, part of it is plugging like your function into something called the difference quotient here. Again, like where it comes from, all that. If you're really curious, you can, and you like know some limits already, you can watch my Understanding Not Memorizing video on it. It's one of my series that I have on YouTube. So let's let f of x equal to, let's say, x to the fourth. Evaluate f of x plus h minus f of x over h, comma, h cannot equal 0. Hopefully that makes sense, because if you plug in 0 in for h, then it would be undefined. So where do we go from here? Well, you have to think about function notation, okay? We see an f of something, right? An f of something here. Okay, so really how I want you to think about this is, if it's f of x plus h, think of it like plugging in like f of 3. For example, f of 3, f of 3, that's just 3 to the fourth. Same sort of concept here. It would just be x plus h to the fourth minus f of x, which is x to the fourth over h. Right? That should make sense, right? F of x plus h, that would just be x plus h to the fourth minus then f of x, which is x to the fourth over h. So where do we go from here? The ultimate goal with the difference quotient is that the h in the denominator should cancel out. We want the h in the denominator to cancel out. The h has to always cancel out. The h will always cancel out. Okay, and when the h cancels out, that's when you know you're done. Okay, so we have this over h. So the only way to actually do this is to FOIL out x plus h to the fourth. Well, if you memorize the formula, a plus b to the fourth, you could do it. Or we could just use Pascal's triangle, right? So we can just do this, like we know we want to go to row 4 because of degree 4, so it'll be, the coefficients will be 1, 4, 6, 4, 1. And then, I wish I had more space here, minus x to the fourth. And yeah, I'm going to erase the rest because hopefully you understand where I'm getting the 1, 4, 6, 4, 1 from. Okay, Pascal's triangle. Okay, I'm just going to erase it here. Why won't it let me erase? This notability has been terrible lately. I don't know why. I can't erase stuff. It's just switching back to my pen when I just want it to be at the, well, I can try this. Will it work? Delete. Okay, that's better. So we know the 1, we have a 1, a 4, a 6, a 4, a 1, then minus x to the fourth over h. So I'm going to let this be like our a term and our b term. So we want to go with like a to the 0, so x to the 0, x to the first, x to the second, x to the third, and x to the fourth. I want to reverse the process with h, so it'll be h to the fourth, h to the third, h to the 0, h to the second, h to the first, h to the 0. And then I want to add all these, right? Add. So then this will then be h to the fourth plus 4xh cubed plus 6x squared h squared plus 4x cubed h plus x to the fourth minus x to the fourth over h. So hopefully you see here that then these x terms will cancel, and that we now have terms we have terms in the numerator all in terms of h. So now we can just divide, like we can split this into separate fractions, h to the fourth over h plus 4xh cubed over h plus 6x squared h squared over h plus 4x cubed h over h. Yeah, and that should be, and then we can cancel out. Again, the more you do this, the more you're like, oh, I just know that it'll cancel the h's, just subtract the exponent by 1 for each term. So what I mean by that is this would cancel, this would cancel, this would be 3, this would cancel, this would be 2, this would cancel, this would be 1, this would cancel completely, so then it'll just be h cubed plus 4xh squared, right, h cubed plus 4xh squared plus 6x squared h plus 4x cubed. And then that should be the answer to your difference quotient. So this is sort of introducing you to what you are expected to do in calculus. You're expected to evaluate the difference quotient, but with a little bit of a twist that you will learn in calculus. Again, if you know what limits are already, again, you guys may all be at different places. You can watch that video in my Understanding Not Memorizing series, which goes over actually getting the limit, definition of the derivative, deriving this difference quotient, and then adding that limit part to it. Okay. So yeah, this is just sort of, again, stuff that you need to know. Binomial, like Pascal's triangle, not necessarily required, but it is a very helpful technique that I would 100% recommend you to know, because it eases out that like foiling process, and it's also an easier way to actually like look at it, and it's also easier to not make mistake. It's much you won't make a lot. You will. The amount of mistakes you will make from foiling out like a plus b times a plus b times a plus b times a plus b will be significantly more compared to if you use like the Pascal's triangle technique, right? The Pascal's triangle technique, I would say, is a lot cleaner, and the foiling process, there's a lot of room for error. So that's why it's good to know, okay? Because your teachers will definitely take off points for algebraic errors. So you got to make sure you master that and use these shortcuts to sort of make it easier for you. Okay, so now LCD / rational expression simplification. This is really for limits, so you're going to learn a little bit about evaluating limits. And you're probably like, at first you are only going to be using like algebra and like some sort of like manipulation techniques to solve them, just using solely your knowledge of algebra and trigonometry. Then later you'll learn a rule called L'Hopital's rule, which makes it very much easier. But again, like first like month of calculus, you're just going to be doing a bunch of limits. So that's why, and they'll expect you to do it using the algebra and trig that you know. So part of that involves like rational expression simplification, and then of course like finding horizontal and vertical asymptotes. I'm gonna go over more techniques though in like a part 2 or a part 3 like of this like these types of videos. So LCD, right? Hopefully you understand that that's just least common denominator. Another way of thinking about it is just the LCM of the denominator, right? You guys know what LCM is, right? Least common multiple, just that of the denominator. So let me make up an example here. You were asked to add x over 3 plus x plus 5 plus 9x over 2 plus x times 6 minus x plus 7 over x, and you're asked to add this. Okay, so if you're asked to add this, again, let me rewrite it in black here. X over 3 plus x plus 9 minus 2x over, I don't know, let me just what did I even write before? Let me just trace it with black, because the thing is, blue is usually like my annotation color. So I don't know. Seven over x. So really, the best way to find your LCD is to literally just multiply all your denominators. Okay? Your LCD, the best way to find your LCD is to just multiply all your denominators. But again, if you see any factorization that could go on within your denominator, like for example, if you have x, if we added another term here, like a 9 over x squared minus 6x plus 9 term, you're going to want to make sure that you factor this. And if not, then this is just, you have to treat this like another factor in a way. Okay, if it was not factorable. Okay, so we're going to deal with this for now. Okay, so really our LCD, we just multiply all the denominators. So it should just be 3 plus x times 2 plus x times 6 minus x times x. Okay, so now we just want to get, like, we want to have an entire fraction with this denominator is essentially what we're trying to do. So now what do we need to multiply 3 plus x by? This fraction to get that, this fraction right here to get that denominator. We have a 3 plus x already, so I'm just going to multiply it by the numerator and denominator by 2 plus x times 6 minus x times x. I want to multiply the numerator as well, 2 plus x times 6 minus x times x with this guy right here. Here, I see a 2 plus x and a 6 minus x, so I'll just multiply numerator and denominator here by x. X times 3 plus x. And I see here times x times 3 plus x. Then here I have an x, so I should just multiply this by 3 plus x times 2 plus x times 6 minus x here. So this would be times 3 plus x times 2 plus x times 6 minus x. And then you will get this entire fraction here. And before, you can, again, like, sometimes they expect you to FOIL it, sometimes I'm not going to FOIL the numerator, like FOIL each individual term of the numerator for the sake of, because again, I expect you guys to know how to do that already. And again, what I'm talking about here, let me just write it down here. This is our LCD, so then we'll have this big fraction of 2 plus x times 6 minus x times x plus 5 plus 9x times x times 3 plus x plus 7 times 3 plus x times 2 plus x times 6 minus x. So this is, like, again, we're putting this into one complete fraction. If you think about it, this is the same kind of process if you were to add 5 over 9 plus 7 over 2 plus 3 over 4. The common, like, denominator here, that, like, the denominator you could get here is like 9 times 2 times 4 as your denominator, and then the numerator, this would be I want to do 5 times 2 times 4 plus 7 times 9 times 4 plus 3 times 9 times 2, stuff like that. It's the same type of process as if you were doing it without using algebra. So it's just, you have variables and you're applying the same process here. Again, I'd expect you to, like, know how to do this, the foiling of these, because then, and of course to FOIL out these as well, and because then if for example you were to find, like, the limit, you guys don't know limits yet, but, like, if you were to find the limit as, like, say x approaches infinity, you would need this to be, or you would want it to be, like, out of its factored form to make it easier on you. Okay, so this is just LCD. Should have that, like, you should know it already. It's probably the easiest, or probably, I would say the last one's probably the easiest to know. But again, these are just techniques. Again, you probably learned already Algebra 1, Algebra 2, just going over it because it's super important that you know it, especially when doing limits in calculus. So number 4, finding horizontal and vertical asymptotes for limits. So this, again, very short. Let's say we have some expression or some, let's say we have x cubed minus 6x squared plus 9 over 7x cubed. Okay, so we want to find both the horizontal and vertical asymptotes. So it's kind of leading you to limits. We'll find horizontal first. The horizontal asymptote really guides the end behavior of a rational function. Okay, the horizontal asymptote like guides the end behavior for the rational function. So if you think about it, like when you do a limit, right? Again, why am I bringing up limits? Like it'll be like just approaching infinity. When this rational function, when the x's approach infinity, I'm just going to write as like an x approaches infinity, right? Just when x approaches infinity. Hopefully you're familiar with this from like end behavior stuff. When x approaches infinity, it will approach that horizontal asymptote. Okay, just when x approaches infinity, that will equal to the horizontal asymptote. So when this rational function here approaches infinity, it'll equal to the horizontal asymptote. So how do we find the horizontal asymptote? Well, we want to first put the numerator and the denominator in standard form if we could. Remember, term with the highest degree first. Okay, so we see here we have x cubed is the highest degree term in the numerator, and x cubed term is the highest degree in the denominator. We take the coefficients of those the highest degree terms here, right? This would be a 1, and this would be a 7, and the ratio between those two will equal to this. So this would then be 1 over 7. That's our horizontal asymptote, and when x approaches infinity of this, it will then equal to 1 over 7. Okay, so that's really the gist of it. The horizontal asymptote guides the end behavior of the function, and it's the ratio with both of the coefficients of the coefficient of the numerator with the highest degree term and the coefficient of the denominator with the highest degree term. It's that a ratio between the two. Okay, from numerator to denominator. So that's really it for horizontal asymptotes. For vertical asymptotes, you want to set the denominator just equal to 0. Okay, you have to set the denominator equal to 0. So in this case, we just set 7x cubed equals 0. We know that x equals 0, so we can therefore say x cannot equal 0, because of course the denominator is or if the denominator equals 0, then it's undefined, and that's like the vertical asymptote. Okay, that's where the vertical asymptote will be located. Sometimes you will have cases where you'll have something like this. You'll have a let's see here, x plus 7 times 6 minus x over 6 minus x. Okay, what do you do here? So you see that this guy in the, first thing you'll say is, like, to find the vertical asymptote, yeah, I have to set the denominator equal to 0. I'm going to let 6 minus x equal 0, so x equals 6. That's where a vertical asymptote is. But that's not quite true if we see that this can actually cancel with the numerator. Like we see a 6 minus x here and a 6 minus x here. These cancel. So what does this actually leave us with? Well, it leaves us with the line y equals to, or it leaves us with the x plus 7. So it'll look something like this. Okay, so this is not where a vertical asymptote would be. It would just be, it would be like this is 7. This is what the line looks like. But it would have a hole, like a hole here at, like, let's say this is 6. Again, not really drawn to scale. But if this is 6, there'll be some hole here. So the function is only undefined at x equals 6. and there's no vertical asymptote. So really, you have to be careful here. Another example, you have like x squared minus 6x plus 9 over x minus 3. Okay, you cannot immediately check, or you cannot immediately set the denominator equal to 0 unless you first check that, hey, the numerator is factorable. Do any of the factors like cancel with the denominator? So in this case, this would be x minus 3 the whole cubed over the whole squared over x minus 3. We see that the denominator will cancel, and this would be 2, so it'll just be x minus 3 the whole squared, and it would have a whole at x minus, or at x equals 3. It would have a whole, not a vertical asymptote. So in this case here, you see that nothing cancels. So if this numerator, which is not factorable, which is not factorable here, you can immediately say that this will not cancel with this. And even if it was, just you can still obviously see here it won't be canceled with the 7x cubed. So therefore, you can just set the 7x cubed equal to 0 in order to find your vertical asymptote. Okay, so yeah, these are just 4 techniques you should sort of know. I will, of course, post more techniques because these are not the only 4. There's a bunch more you need to know. And again, I'm gonna only cover the relevant stuff that you like need to know, or it will be very, very beneficial to you. You know, especially like once you get into calculus, you'll just be like chilling, you know, because you know this stuff already. All right. Thanks for watching. See you guys in the next one.